15 minuti, al 3 ti do i 3.
And in this talk I will present on behalf of the Vegas team the results of the photometric analysis performed on NGC 4472 in Virgo, also known as M49. I will first briefly present the survey and its science aims. Then I will show you the results and the conclusion of our work, and finally I will talk about some future plans. Vegas stands for VST Survey of Elliptical Galaxies in the Southern Hemisphere, and this is a multi-band survey of about 100 galaxies in all environments, from field to clusters. This is an example of our data, and this is the status of the survey up to period 94. While in period 95, just 1 week ago, we have observed about 70% of the Fornax cluster. We plan to invest 350 hours of observing time at VST over 5 years to perform this survey, with the main goal to obtain surface brightness profiles above these limits. In this way, with the total exposure time per pointing in each filter of about 3 hours, we will obtain a complementary survey in the Southern Hemisphere of the new generation Virgo cluster survey with comparable depth but with no restriction to the environment. These are the main science aims of the survey that have been already shown by Michele Cantiello yesterday, but my work is mainly focused on the surface photometry of galaxies. So, to the study of surface brightness up to 10 effective radii and the correlation about structural parameters. As well as to the study of color gradients and their connection with the galaxy formation theories. So why NGC 4472? This galaxy can be considered a test case. First of all, because there is an ample and excellent literature that is useful to make comparisons. Then, because this is a nearby and very extended object, and this will allow us to test our data reduction procedure and mainly our background subtraction strategy that, for bigger objects can be an issue. Finally, because we have, in this way we can have a direct comparison with NGBS, and most of all because there are many smaller galaxies, many smaller early type galaxies in the field around NGC 4472 that we can also study. All the data analyzed in this work, and actually all the Vegas data, have been reduced with the VST tube, which is a pipeline developed in Naples by Aniello Grado and Luca Limatola. And this pipeline starts from raw data and gives us reduced and fully calibrated images. We also have many reports on data reduction with many quality control plots, and the pipeline also includes a growing set of analysis tools, many of them especially developed for Vegas. So the first step of this work has been to obtain a surface brightness, azimutally average surface brightness profile in the G band, and that is compared in this plot with the literature. Of course, all the other profiles have been shifted to the G band by applying a suitable color offset. The first thing that we can see from this plot is that the agreement with the literature is excellent. Another important thing is that we have reached the main goal of the survey. But as I will show in a few minutes, we are also better than this. Just to give you an idea of the extension of this galaxy, this is the isopod corresponding to the last point of this plot. If we look at the residual of the mean profiles from the R to the 1/4 profile best fitting the main galaxy body, we can see that there is a bright nucleus and this wave pattern. The black line is the same plot obtained by De Vaucouleurs and Cavaccioli in 1979 for NGC 3379. As you can see, there are clear similarities in the behavior of the residuals. Recent studies on NGC 3379 have shown that this galaxy has different substructures such as plumes and shells of diffuse material. And this behavior seems to be typical for galaxies with this kind of substructures. As I said before, we are better than our goal. And in fact, if we extend our analysis to the very faint outskirts of the galaxy, we end up with this kind of profile. As you can see, the shape of the profiles, both in the G and in the I band, is very similar to the profile shown by Alessia before. In fact, if we compare this profile, in particular in this region where we see a change of the slope at a magnitude of about 27 in the G band and a flattening of the profile above this limit, if we compare this profile with those obtained by Zivetti et al. In 2005 for intracluster light, you can see that there is a good match in this region between these two profiles. These features, in fact, are typical of the presence of intracluster light. To better analyze the light distribution of this object, we have performed a two-dimensional model of the galaxy and subtracted it to the G-band original image. These are the residuals that clearly show the presence of shell-like structures as well as these fans of diffuse material. Another feature that stands out from this image is this tail, which is due to an ongoing interaction with the dwarf irregular galaxy, UGC 7636. Another way to better emphasize this tail is this. If you flip twice the image of the galaxy about the center of NGC 4472 and then subtract this to the original image, this is what you obtain. As you can see, there is a clear asymmetry in the nuclear regions due to the presence of a boomerang-shaped dust lane already detected by the NGVS team, and this long plume twisting about the center of NGC 4472. We also analyzed, of course, this dwarf galaxy, and of course in this case we have to assume fixed ellipticity and the position angle, and we derived this G and I band surface brightness profile, which clearly reflected the very perturbed structure of the galaxy. And in the outer regions, of course, they are affected by the halo of the big galaxy in which this is embedded. However, we have been able to obtain also color profile, mean color profile of this galaxy. And as you can see, the galaxy is very blue, and there is almost no color gradient except for these regions. Of course, above these limits, uncertainties are too big to derive a reliable color estimate, but I want to stress that this limit corresponds to a G-band magnitude of 27, so they are very deep. As I said, around NGC 4472 there are a number of early type galaxies that we can study. In case of these smaller galaxies, of course, the background subtraction is not an issue and is more accurate. And in fact, for NGC 4434, we derive very deep surface brightness profile. We are almost at a magnitude of 13 in G. And also in this case, there seems to be an indication of intracluster light. But this is something that we have investigated because this galaxy is also at the edge of the frame, so we have to better investigate this point. However, also in this case, we have a perfect agreement with the literature, and we have derived a color estimate with very relatively small uncertainties. The same has been done for NGC 4464, and in this case we obtain even deeper profiles with small uncertainties, and in excellent agreement with the literature also in this case, and we obtained a color profile, mean color profile, which is similar to those obtained for the other small early type galaxy. So, in conclusion, we have reached the goal of the survey. We have been also able to detect intracluster light in the surface brightness profiles. We have detected shells and fans of diffuse material in the two-dimensional residuals that are also confirmed by the wave-like pattern in the one-dimensional residuals. And we have been also able to obtain deep surface brightness profile and color gradients for small early type galaxies in the field. Even if we are satisfied with these results, we will further improve. We want to further improve them. And in fact, we plan to adopt a near-infrared-like observing strategy, which is, of course, more expensive in terms of observing time, but will allow us to reach very faint surface brightness level and, above all, to significantly reduce uncertainties. Of course, this means that in the future we will have a lot of work to do. And I'll stop here.
Thank you, Marilena. I took it so on time. Question?
I want to ask if you reach the cluster light level around several galaxies, then you might believe that you should find the same color, the ICL, independent of where you see it. Is that true?
Yeah, yeah.
I would like to know if you detected compact dwarfs or low super-brightness galaxies in your survey.
Yes, we have a lot of such galaxies in our.
Did you compare your results with the results of the survey AGS?
For this galaxy, yes.
For the compact?
No,
dwarfs?
not yet.
Because they detected several of new this kind of objects in the area that was not detected before. So I would like to know if you confirm the results of.
No, we detected galaxies because, as I said, we have a survey of comparable depth, but I have not yet done this.
Thank you.
The next speaker is Daniela Bettoni, telling us the properties of faint galaxies in nearby clusters.
Thanks to the organizers to have allowed me to talk today, and congratulations to Massimo. And I would like to start my talk on this subject with the third slide, in which I remember your work on this. Okay, I would like to talk today on the faint galaxies that we found in the our survey, of wing survey. In one slide, I give you a flowchart of what we have done and what were the purposes of our survey. So, to have a local reference for nearby cluster, 76 clusters, for which we have imaging to derive all the photometric data that we can, and then a follow-up spectroscopic plan to have the redshift and also to measure the fundamental plane. That is the main focus on the dwarf galaxies that today I would like to talk to you, and I would like to show you which is the characteristic of the fundamental plane of dwarf galaxies. I would like to point out that we have the first release of all our data. We published a lot of catalog in the course of this year, but finally, at the end of this year, with Alessia Moretti, we were able to release all the catalogs that are available through the web. Here, a list of the products we used, and that I will use today to show you the properties of our faint galaxies. First, the imaging that we started with the two wide feeder imagers, north and south, at the beginning of the survey, and then now we have the extension, the Omega Wings survey, in which we use VST plus Omega Cam to enlarge the sample, and you have seen the beautiful images that Bianca has found in the outer region and also in the central part of the jellyfishes. And then we have the redshift complete for almost 50%, with the 50% on completeness, and then we have the massive star formation rate ranges in the two papers that you have seen here, the gas photo, which is the photometry, in which you have also the reference, and the morpho data, which is a very huge work that Gianni Fasano has done to do automatic morphological classification. Finally, this is the number of galaxies that we have with all the measured parameters that are the galaxies for which we have the spectroscopy. And if you want to assess all the data, this is the query you have to do in the registry using TopCat. If you give this query, you can access also all our data, the one for the first release of WINGS that are available for all the community. A background. So, first point is that in the Cormedy relation, the faint galaxies seems to be in a different place. And I would like to start with this, Massimo, in which you was one of the first that collect altogether a lot of data from Virgo and the common literature, in which you can see that galaxies, small galaxy and faint one, have a different position in the relation, and then are a different population. What we want to investigate, this is a plot that has been produced in many times, and you can see in a lot of papers, but when we are going to the fundamental plane, you lack the velocity dispersion. When we start to see the value of the velocity dispersion that you expect for this kind of objects, you have values below 50 km per second. So it became very difficult to measure. You need high resolution spectrograph. And I would like to show a little bit some background on the characteristics of those galaxies. Also, as today, Mauro Donofrio tell us that the Stersic index seems to be around 1, 2, and then the Faddereck-Jackson relation seems to be different from the canonical one with the power of sigma 4. And finally, when Mauro, using the WINGS data, we studied the fundamental plane, we have the indication that probably this is the result of our study of the fundamental plane, in which the two colors are related to the fact that we use the velocity dispersion from Sloan or from the know-how fundamental plane survey. And you can see that if we look at this region, which is the one in which we expect to have the faint object, is empty, because of course we have the photometry from the WINGS survey, but we do not have the velocity dispersion because of course Sloan, NORLOA, and the know-how fundamental plane give us the data. And this is true also in this projection of the fundamental plane. What we want to do is that, however, Mauro proposed that there is some indication that probably is not really, the faint objects are not really on the canonical fundamental plane. And this is confirmed in recent years by the studies that have been done in Virgo, Coma, and Fornax, the nearby cluster. This is a result that I found for Coma, in which you can see that faint galaxy seems to deviate from the line of the fundamental plane. But we are very nearby. So for the first time, if there is the possibility to obtain the velocity dispersion of the galaxies we have in our sample, we can have a confirm of the fact that the fundamental plane in the faint region deviates from the canonical one. And this is our goal, that we want to measure the fundamental plane for those galaxies, and then using high-resolution spectra to derive a very robust star formation history and stellar population for those galaxies. And we started this using X-shooter, because X-shooter has the possibility to reach an instrumental velocity dispersion which is below 30 kilometers per second. And we had 4 observing runs in GTO, 3 observing runs, sorry, and 4 nights. 1 was completely lost for bad weather, and then we obtained our sample. We started with a sample of 45 objects, 45 only because we need to be sure that our galaxies belong to the cluster. So we selected only galaxies for which we have a spectrum, and so the redshift. And then in the range of magnitude -15, -16, and this redshift in the range of -16, -17, and this range of redshift. The galaxies were selected non-interacting, and the surface brightness was brighter than 19.5, and no constraint on morphology. And this means that we have in our sample also one galaxy which is classified by Gianni Fasano, which is our classifier, is early spiral. And then we ended with 27 targets. Unfortunately 4 resulted not to be members, were galaxies at redshift 0.1, 0.2, and then this was due to the fact that they are very faint, and our fiber spectra were very noisy. And then the final sample is composed by 22 galaxies, and for 4 of these galaxies we have also the emission lines in the nucleo, emission lines that were not visible in the low resolution spectra. And I will show you this is an example of how they look like our spectra, and the line you see is in the exact shape of the slit, and so you can see that the galaxy is all inside the slit of the shooter, so we can measure the velocity dispersion of the whole galaxy. Here an example of our spectra. This is one spectrum in the blue region. This is a comparison star to see how they look like. We planned to measure the velocity dispersion using X-shooter, also using the infrared part, to use the CO lines of the stars, but the galaxies were too fine to have a measurable infrared flux. It was black, and so we were obliged to work only in the blue region. And we obtained here the example of the emission lines, how they look like. You can see that they are inclined, so they rotate. In general, there is a very small disk in which you can see the rotation is around 30 kilometers per second in the inner 3 arc seconds. And here you have the fit of the stellar templates to our spectra. You can see that we have a very good fit. This is a galaxy with 44 high velocity dispersion, but this is one of my favorite. So 22 kilometers per second of velocity dispersion with a very low error, and you see there are emission lines that we mask, and the galaxies has a younger stellar population, and we were able to fit, thanks to the library because of a shooter that it was recently published, because we observed a set of stars to use as the plate with this instrument, but we lack this kind of very young stars that we use from the library, and it works very well. So, finally, the main properties of the sample. We have an average velocity dispersion. This is the histogram of velocity dispersion around 38 kilometers per second. The absolute magnitude is in the range that we expect, minus 15, minus 17, and also the Celsius index is 1.6, the one we expect for this kind of object. And finally, I would like to point out that also the ellipticity, the average ellipticity is very low in the sense that they're very round. And this is a comparison I've made of the Fabre-Jackson relation. The red points are data that I found for coma, and the blue points are our data. And this is the fit to our data that confirm the fact that the slope is not 4, is around 1.5, 2. And here, the fundamental plane. First, this one, which is the Fabre-Jackson relation. The black points are the old WINCS data that we use to measure the fundamental plane. The red ones are our dwarf galaxies. You can see they are really in the region which we expect, and we can say this is the classical canonical relation, this is the 1.6, it's a very strange point. This is the Cormendy relation, and they are where we expect, of course, and finally, if we put the effective radius against velocity dispersion, this is very interesting because it seems that there is a continuous line in the low region of velocity dispersion and radius. And here we have the same with respect to the mass, the stellar mass that we derived with our low resolution spectra, and you see how they place in a very different region with respect to the so-called normal early type galaxy. And this is very interesting to me because it's the velocity dispersion against age. You can see that the galaxies are very young, and the oldest one are the only one that place close to the points of the big galaxies, of the family of normal early type galaxies. This is the so-called photometric fundamental plane, in which the data are placed on with respect to logarithm of the Celsius index, not velocity dispersion. This can be done without the need of the velocity dispersion, but you can see that, again, the galaxies are really in a region different in most part of the plane. And this is the fundamental plane. As you can see, we have that our galaxies deviate, strongly deviate, at least in the part. And you can see here, if you place the effective surface brightness, you can see the faintest one deviate more from the zero line, and also for the velocity dispersion, the one with the largest velocity dispersion are more, the deviation is larger for those ones. And finally, this is the classical canonical fundamental plane that seems to give the idea that the suggestion of the paper of Mauro that possibly there is some kind of curvature of the fundamental plane could be present. 22 points are too few, I understand this, but the indication is very strong. In this region, very few points are available at this distance. And so I came with my conclusion, our result that seems to confirm that the faint galaxies do not follow the fundamental plane, and they confirm also that mass ratios varies with the inner superbranch, and the indication of the paper of Mauro that the faint tail of the fundamental plane is increased seems to be confirmed. Thanks.
Thank you. Question?
that the difference is in the relative content of dark matter?
We have not investigated till now the presence of that, because I was obliged to add all together the spectra, so we have only one measurement of velocity dispersion, long rotation, so we have to do a model to try to see, but we have not investigated.
Yeah, because we are comparing things that are related to the variance with things that are related
yes,
to the
probably
mass.
this could be a good way to understand it, to interpret the data, yes.
I have just a curiosity. Did you investigate the role of the Changhai enhancement in your fundamental plane?
No. Okay.
Thank you.
So now we move to hierarchies with the contribution of Adriano.
Come? Sì, sì. Okay, first of all, I thank the organizer for giving me the opportunity to make this talk, and first of all to greet Massimo and make my personal wishes for his future brilliant career. I will bring you to a completely different scientific context. We have seen so many detailed results on the galaxies in the nearby universe, and I will move you to the high redshift universe and to see where all this game started some billions of years ago. It looks like it's impossible to start this kind of talks without showing this popular diagram showing the concept that we are observing here, the local universe, and then as we move to observe galaxies which are farther and farther away, we approach the first stages of the evolution of galaxies down to the so-called dark ages where they were essentially the first light started to shine. I want to give you a completely different taste of this game. This is a comparison between, just two pictures. This is a picture of a nearby galaxy taken from the Atlas, and so these are the kind of objects we can study in many details in the local universe. And of course, we have seen over this week how many results we can get in these cases. On the other side, the red dot you don't see here is a galaxy at redshift 6. You don't see because this is everything we can see are is just a bunch of photons coming out from this very, very faint target. So the only chance, in some sense, it's an extraordinary result that we can observe these galaxies. But the price we have to pay is that we can, just to detect a very few photons, what we have to do is to use as much as possible all the available facilities on the ground and from space to detect these galaxies and to collect very few photons, but all the available information. And so this is the kind of exercise that is currently ongoing. So the idea is to use all the facilities, all the possible facilities to study very few selected area in the sky as deep as possible. So these ultra-deep surveys are probably one of the latest, I would say the latest and the more ambitious ever taken with Space Telescope Iskanders, which is a large collaboration of people in many continents, and is essentially based on coordinated observation with space telescopes over 5 different fields, which are very popular, the usual BOOTS, Cosmos, AGS, and UDS. And they delivered very deep mosaics of these areas. This is the near-infrared area. And with even regions which seem, of course, blank, void in the images, of course, go to the extreme redshift. And again, if you look at the faintest targets in the images, again, they are small dots we can barely see in the images. So the idea is, even in these cases, since we want to go as deep as possible, is to develop this concept of the wedding cake strategy, where you can go from extremely deep surveys like the ultra deep field, which means you take a very deep exposure over a single point in the sky, and then you try to assemble larger areas, of course, with decreasing depth over as you increase the area, in order to sample the distribution of galaxies of different luminosities. As I said, it's not only HST playing is not the only HST is not the only instrument playing in this arena. You have to use all the possible telescopes to observe these galaxies, and in particular there is, of course, a space telescope cannot go beyond the H-band, and so it was inevitable, I would say, to submit a large program at ESO to use OCAI, which is by far the best infrared imager on the ground, to observe the fields which are observable from the south. And so I led this large program over the last 3 years. This is the outcoming image in the good south area. This is really the deepest image you can get from the ground in the K-band. Just to give you an idea, the central area, the exposure time is close to 100 hours for each pixel. And if you look at the outcome, this is a comparison between the image in the HST and in the VLT images, one in H and one in K. And as you can see, I mean, the comparison is really astonishing. So you take a while to realize that this is the HST image and this is the OCAI ground-based image, and this comes from, if you look at the numbers, the final seeing is better than 0.4, and the magnitude limits are of the order of 27th magnitude in the K-band, AD, of course. So this data is actually public since a while, since a couple of months on the ESO archive, and there is a paper out describing these. So these are all public data, and I will show you later how we have made use of this data in particular. Now let's come back to the science. What are the real questions that we have? Well, broadly speaking, there are two questions when you move to the extreme redshift. There are, broadly speaking, two questions to address. One is how galaxies formed. So what are the early stages, the physical processes that in the first stage of galaxy evolution? And the second is which sources reionized the universe. You know that there was this transition between a early stage where the universe was opaque to the UV radiation to a phase later on where it became transparent. This reionization is a process. I will not. Unfortunately, I don't have the time to show results on the latest situation on this aspect, but I will be happy to address a question if you have. The point is that, again, as I've shown you before, we don't have the capability to observe individual galaxies in details. Okay, that would be the real way to address this question. So we cannot do that. So what we have to do, we have to collect and possibly interpret large statistical samples and try to understand what's going on. And this I will try to give you an update of where we are thanks to candles and similar surveys. Quite briefly, we know that we detect, we identify better high redshift galaxies because they are strongly observed. So if you look at the spectrum, for instance, of a galaxy of redshift 7, this red line here, this is a simulated spectrum, and you have a complete absorption shortward of the Lyman alpha line, and this absorption is due to the intergalactic medium. So if you go back to the images, this is what you expect to see. Is in the various images, as you go to higher and higher redshift, you have objects that you clearly detect in some bands, and then they disappear suddenly as soon as the break comes inside the filter you are using in the observation. So this technique, the Lyman break technique, is very well verified up to redshift 6 and slightly above. And so we believe it's a robust technique to identify galaxies up to very high redshift, in principle, down to redshift 8 or even 10 or 15. So this way we can identify, select, and then compile statistical properties of these galaxies. So this is the latest picture. The first and most obvious statistical sample you can use is the luminosity function, which is simply the number of galaxies in a volume of the universe as a function of the UV magnitude. Of course, as I've shown you before, we observe only the rest frame very far UV part of the spectrum, so we are essentially sensitive to not to the part of the spectrum which is not absorbed by dust and is due to star formation ongoing in these galaxies. So we can compile luminosity functions as a function of the absolute UV magnitude once you correct for the distance. So the latest kind of points are the red dots, and there is a wealth of previous surveys, which are all the other points, and the interesting, including one you see here, Castellano, which was based on our early VLTO kind data. And what you can see is that in general, despite the extreme challenges involved in this kind of analysis, the overall picture is reasonably consistent. Okay, different surveys, different groups, different simulations, because you need simulations to interpret the data, blah, blah, seems to conspire and produce a consistent picture of the evolution of the luminosity function at these early epochs of the universe. You can see already by eye that there is an evidence that the luminosity function evolves, changes from redshift 6. Redshift 6 is of the order of 1 giga-year after the Big Bang, and down to 600 millions of years. And you see that there is a clear evidence of an evolution, and you see much better in this plot, where you see the evolution from redshift 4 to redshift 5 is reasonably smooth. Is not, of course, perfectly stepped. You don't expect that. But there is a clear evolution, and there is also an evidence, as you may see here, that bright galaxies, I will come back later, I think, there is an evidence, a clear evidence that bright galaxies, which are these, are evolving faster than faint galaxies. So from redshift 4 to redshift 8, we are seeing the epoch where bright galaxies are essentially forming, and they become brighter and brighter, and I will show you later more and more massive over time. So you can try to quantify this in more detail, and let me go back one step. So in some sense it's already an exceptional result that you are able to map and reconstruct the history of the universe in these early epochs. And as I said, these are statistical samples. So the question is, how are individual galaxies evolving? Should they evolve to reproduce this behavior? So if you go to very high redshift, so the next, the last step we can measure with some statistical reliability. This is the luminosity function on redshift 7, I showed you before. This is the redshift 8 luminosity function, the line that we have measured. And the dots are computed in assuming that the luminosity function at redshift 7, each galaxy evolves simply with a simple scaling of the star formation law. So it's a so-called luminosity evolution. So you simply assume that all galaxies, all bright galaxies are in place, are there. Merging between galaxies is not important at in this epoch. Each galaxy is simply becoming slightly fainter, going back in time, consistent with a star formation rate that increases with time coming toward us. Okay? So with this simple assumption of a luminosity evolution, you can see that for bright galaxies, this evolution matches very well the observed data. So the simplest interpretation, and this is a robust result only because we have a good statistics here, and we can rule out different scenarios. Probably is not true for faint galaxies, by the way. And so this is telling us, is the simplest way to interpret the data, and is telling us something about how the individual galaxies change in time. And I could show, I have a plot I'm not going to show, but we can discuss later, that this is exactly what theoretical models are supposed to predicting at this moment. Okay, so we have the bright galaxies are the center of the biggest halos at these redshifts, and they are accreting gas, and this gas is pumping up the star formation rate with time. So this is, at least in qualitative agreement with the current theoretical models. Before you claim victory, you have to go back again and see other predictions of the models. And in particular, you can ask yourself if these models do predict the luminosity function. And so you can see here the dots are the observed data at different redshifts, and the blue dots here, the red dots I meant, the blue dots here are the predicted luminosity function from theoretical models without including any amount of dust in galaxies. So if you can clearly see that, especially at, let me say, not too high redshift, 4, 5, and 6, the disagreement is very clear, and the green dots is the corrected luminosity function once you include dust in the galaxies themselves. And as you may see, you have to include a substantial amount of dust, an amount of dust which decreases as you go to higher redshift. And this is also, there are many papers by the Varn group on this point in particular, and the problem here is we don't see this dust in galaxies. So when we observe high redshift galaxies, they tend to be dust-free. We don't see all this dust in Lyman break galaxies that we observe. So this is this tension between this is inevitable in models, because every time you have star formation rate, you immediately form, as you know, dust. So it's very difficult to decouple dust from star formation rate after 1 giga-year of the universe. So this is, in some sense, is a robust prediction of this model. And nevertheless, we don't see this dust in the galaxies themselves. So this is a red flag which is telling us that something is not completely understood. How much time I have? Okay. And so if you want to understand, to collect a different observable, you can look the other way around. Rather than looking at the star formation rate in individual galaxy, you can try to estimate their stellar mass and see whether the evolution of the stellar mass in time is consistent with the evolution of the star formation rate. Of course, this is the popular Madal diagram, star formation rate as a function of redshift. This is the analogous in stellar mass. This is the amount of stellar mass as a function of redshift or of look-back time. Okay? And you expect, since one is just a derivative of the other, it should be very easy to check whether the two things are consistent or not. And the problem is they are not, as I will show you later. So how can you measure the stellar mass? Again, here is another area where deep photometry is the only tool. This is an example of a galaxy at redshift around 4. You can see the exquisite photometry. This is a really faint object, about 24.5, with a spectroscopic redshift in this case, and you have an exquisite photometry coming from HST, from VLT, and from Spitzer, and you can constrain the overall spectral shape of the galaxy and estimate the stellar mass. So there is a machinery behind this. I'm not going to into many details, but it is possible to constrain with a decent uncertainty the stellar mass of individual galaxy. And again, you can compile a mass function so that the distribution, the number of galaxies in the universe in megaparsec cube as a function of their stellar mass. And this is a very recent outcome of Candles that you will see, I think, on Monday on AstroPH. There is this Graziani et al. Paper just accepted. And the Candles data are the blue dots here as a function of redshift, from redshift 4 to redshift 7, if you believe in these numbers, but I think it's pretty robust up to redshift 6. And again, as you may see, there is more scatter for a number of reasons I don't have the time to describe with previous surveys, but the picture is very clear. So if you take, I don't know if you can see this dotted line here, if you take this line as a reference, which is the stellar mass function of redshift 2, you see that as the redshift increases, there is a very strong evolution in the stellar mass. So what you are seeing here is that the stellar mass of galaxies, or the mass of galaxies, the number of stars in galaxies, is strongly increasing as a function of time. Okay, because these galaxies are actively star forming, and so they accrete mass over cosmic time. Before closing the loop, let me show you also another thing we have found in the candles data that I think, and the Hugs data that I think is pretty interesting. This is just a diagnostic plot. It's the stellar mass as a function of the UV luminosity. And you can see that most of the galaxies follow this trend. These are normal Lyman break galaxies. This simply is telling you that the normal Lyman break galaxy, the brighter it is in the UV, the more massive it is. But you can see that there are a bunch of objects here which appear to be very faint in the UV, but nevertheless very massive. This is not just a noise in the observation. So these are real objects. These are among, in some sense, the reddest and in many cases also very bright galaxies at this redshift, and they are in this region of the spectrum because they are intrinsically very red. These are not the Lyman break galaxies that I have shown you before, but these have a spectral shape that is clearly very red, intrinsically very red. They have a photometric redshift which is pretty high, of the order of 4 in these cases. Some of them are very convincingly fit, like this one, for instance, with the spectrum of passively evolving galaxies, already a redshift 3.7 or whatever. In other cases like these are probably highly star-forming galaxies. These are fit with a large amount of dust. In any case, these are representative of the red galaxy population, already a redshift 4. So already a redshift 4, we clearly see the evidence of red galaxies in place at redshift 4. And they can contribute pretty much to the mass function. So if you ignore these massive objects, you end up with a mass function which is, as you may see, much lower, the red dots, much lower than what we measured. Okay? This happens at redshift 4. So, and this is telling you that with candles and with the VLT data, we start to scratch the existence of this red galaxy population at redshift 4. It looks like you don't see evidence at higher redshift, but in this case we simply don't, which makes sense. Maybe we are going at very early stages of the universe, and so simply there are no red galaxies at all. Or maybe the other possibility is that our data are not red and deep enough to detect this kind of population at redshift 6 or 7. We simply don't know. So let me go back to the star formation rate, to the consistency between the star formation rate and the stellar mass. So this is the stellar mass, how it evolves as a function of redshift from candles. And you have shown you before there is a very, very clear evidence of this evolution. So let's assume for simplicity, but it's reasonably correct, that once you take a given density of the galaxies, okay, you are looking at more or less the same galaxy, the same population, as it evolves with time. So this means that if you take a typical galaxy here, for instance, this is equivalent to say that the galaxy at redshift 6 of this density started from, say, 5 in 10 to the 10 stellar masses and ended up 2 in 10 to the 11 stellar solar masses from redshift 6 to redshift 4. Okay, so this evolution is, let's imagine, it's the evolution of a single galaxy. So this means that you have an increase in stellar mass of a factor of 3, whatever, over the time span from redshift 6 to redshift 4. And this is equivalent to a star formation rate averaged from 6 to 4 of the order of 300 of solar masses per year. Now, do we see this level of star formation rate from redshift 6 to redshift 4? The answer is no. This is, if you go and look at the ultraviolet luminosity function, and you translate it into a distribution of the star formation rate, the typical star, so if you take a density of -5, the typical star formation rate for this galaxy is much less than 100, in the redshift being between 6 and 4. Okay? So there is clearly the star formation rate that we estimate in the UV sample that we observed today at redshift 6 appears to be too low to explain the growth of the mass function at redshift from 6 to 4 again. So there is, again, a discrepancy, a tension between the two different measures. And there are many possibilities, of course. One is that the conversion from the UV to the star formation rate is wrong, so we need to have a higher star formation rate. Or, as I said before, we are missing a substantial population of galaxies which are actively star forming and highly extincted at high redshift, and which may change this distribution. And these are the options listed here. The other possibility is that, when I said large merging, is that this simple assumption is not correct at redshift 5, but I think it is, so it's not a merge. So this is the summary of my talk, and I think it's the summary of, to some extent, of our understanding of the statistical properties of galaxies at high redshift. I think it is extremely exciting that we are able to assemble statistically well understood samples of galaxies already at redshift in the first billion of years of the universe, let me put it this way. It is clear that the highest redshift we explore, even in this case, we still detect red galaxies. At any high redshift, we can observe them. Okay, and so there is still open the possibility that these objects become rarer but still exist at even redshifts larger than 4. The bottom line is that the evolution of bright galaxy is consistent with the luminosity evolution at high redshift, but the match between the evolution of the luminosity of the star formation rate and of the stellar mass function are still inconsistent at some level. And I think I will stop here. Thank you.
Thank you very much.
We compared the stellar mass function evolution with the halo mass function evolution for simulations. In what extent is be compatible with the hierarchical assembly of the interparallel?
It is, in the sense that this assumption here, the assumption I did here, of using a fixed density to trace individual galaxies, okay, follows the fact that you, at this redshift, massive objects match one-to-one halos of a given mass, okay. So don't have a plot in this case, but the notion is that they match one-to-one, okay. So I'm using, in this plot, I am using the fact that you have one massive galaxy for one halo at this redshift.
So you should see the same evolution in this.
Yes, and I don't have the plot, but you can see that. For massive galaxies, of course.
Okay.
Okay, Piano. Thank you very much for the beautiful talk. One question which is dictated by my ignorance of the field. Which is the amount of uncertainty associated with the fact that you compare local universe in one bank with early universe in a different bank, and that associated with the fact that photons are traveling in the early universe and their absorption conditions will be different.
So it's well, I think you need a conference to address this question. The second point, we are using only observations redward of the Lyman alpha, so the absorption due to the intergalactic medium is in practice negligible. Okay, so the comparison between the the high redshift universe and the low redshift universe is tougher, of course. In some sense, you can see when you look at the Madao plot. Of course, you are looking at completely different estimators of the star formation rate. Okay. So far, the different estimators, H alpha, infrared luminosity, UV, whatever, seem to be reasonably consistent up to redshift 2 or 3 or so. Okay, the big question is what happens at higher redshift. Above redshift 3, we have only this UV corrected for dust absorption some way. Okay, and as I said, this is one. We have this tension with the growth of stellar mass and other evidence. So this may be one of the problems in place. I should also say that I have ignored this fact, but all this business is assuming a universal and time constant IMF, which again is probably, I would say, most probably wrong. So it's a simplified picture of this.
It's very interesting you find mostly massive galaxies that are passive.
Sorry, say it again?
It's interesting you find massive galaxies that are passive, which goes a bit against the selection, the way you select, right? Because Lyman break technique is very much biased towards.
I didn't cheat. I just jumped one step. So the truth is, we use a full photometric redshift selection. Okay, so the reason for we can identify these objects is that we have a full sample selected in the H band, and we use photometric redshift to select the objects. For most cases, photometric redshift and Lyman break galaxies give you the same answers. Okay, these objects would not be selected if you just apply a pure Lyman break technique.
Okay. That makes sense. But I think still, what I really wanted to ask in that context is whether you might just be seeing the tip of the iceberg here, and that's seeing quite a large population of passive galaxies you don't see, and that will dramatically change the picture even more than what you already described.
It is absolutely possible. The answer will come with JWST. I can say that with the same data, we have looked at the density of possibly evolving galaxies at redshift 2, where you can go much deeper. And there is a clear, very unfortunately, I can show you the plot later. It's a paper on the Astro PH already accepted. And there is a very clear decrease. So looks like only bright galaxies are passively evolving at redshift 2. Okay. But passively evolving galaxies, BZK passively selected galaxies, for instance, are only bright galaxies, and their number density drops significantly when you go faint. Okay, but this is a redshift 2, so the answer is yes, it is possible.
Okay, the last short question.
So, can I ask you to clarify something for me? At the beginning of your talk, when you first showed all of the luminosity functions together, you sort of quickly said that there wasn't necessarily a very, that one, back one, the other direction, there. That there isn't a very continuous change in redshift between those luminosity functions, like you said, nor would you necessarily expect there to be. I mean, naively looking at this, I see a lot of change between redshift 8 and 7, and redshift 7 and 6 looking very similar, and a lot of change between redshift 6 and 5, and redshift 5 and 4 looking very similar. What is that supposed to be telling me? That the error bars are very correlated in these diagrams, and those are more certain than we think, or what?
It's a combination of things. First, the time does not change linearly with redshift. Okay, so first. Second, the overall evolution of the star formation rate does not need to scale linearly. So if you go down to redshift 3 or so, the idea is that in general you have a very slow evolution up to redshift 5. Okay, so even the redshift 3 luminosity function and redshift 2 luminosity function are more or less here. Okay, this because you are entering in the peak of the star formation of the Madau diagram. Okay, so when you are in the peak, these evolutions are smooth. Okay, so then you may have, of course, fluctuations. This is, after all, based on relatively the stability here, I think, is well assessed. There may be some noise, of course, of different sources, as you mentioned here. Okay, so maybe, to me, the redshift 6 is still debated, so maybe a bit higher, and so could fill the gap a little bit. But I think to really get down to this amount of details, we probably need even larger sampling, and probably the data coming from Ultravista will tell us more about the redshift 6 luminosity function.
Thank you very much, and we'll come back in 30 minutes. coffee break, and in 30 minutes we come back.